Before we get started, let's go through some of the basic fundamentals of the OS architecture. Whenever you use Windows, Windows has two different core. One is the user land, the other one is the kernel land or the kernel mode. The kernel mode is where you have unrestricted access to everything. That's basically where your drivers lie, and they have access to full control as to whatever they want to perform, execute, kill, or start over there. Things change a bit when we talk about the user mode, because in user land, one sec, yeah, because in user land, most of the things that we do, they are limited in nature. You cannot execute everything that you want. You will never have full privileges to the lower level. Even though if you are an administrator, you cannot still modify some specific parts of the kernel dispatcher or how they actually interact with the user land, and that can be only done into the kernel part. We are mostly going to take a look at the user land portion that we have, because that's where we have most control of when we are actually dealing with different types of payloads or building tools and techniques. Now, your Windows system has a few different things when you create a process. You have a thread and then you have a process. For a kernel, every process is like a thread in itself. All the threads in a current system. Sorry, Alex has a question. With HVCI and Windows, you can't access the physical address on kernel because in ring zeros understood access to hardware it is more difficult. Yes, that is correct. The HVCI with the due to the introduction of HVCI sometime back, that did change a bit, so you cannot directly access the full hardware. That along with patchguard does restrict a few things that you can actually modify in the kernel mode, but it still allows you to do a lot more things. So is because currently we are not actually worried about managing or modifying the hardware, because most of the time that is specifically I would say limited to what your drivers do. Like for example, you have NVIDIA drivers. I'm not talking about your EDRs in general right now, because they are probably one of the aspects of information security. But when we talk about computers in general, there are a lot of other drivers which usually require access to your low level architecture. That's your hardware, which is what your NVIDIA drivers or your AMD drivers eventually do. And that's where but however, since we are not focused on that, since we are more focused towards uh, actually exploiting the system, gaining access, maintaining persistence for some time, we are never bothered about maintaining persistence for a long or a really long amount of time, even though that is still doable at certain times by using maybe vulnerable drivers or side loading a specific driver, or maybe customizing a specific service based rootkit to make sure that your services cannot be uninstalled unless until the system is formatted. And it doesn't matter even which drivers you install or which drivers have access to the hardware level as well, because in the end, if a system is re-imaged, then you will not have any type of backdoor in it. I mean, there's no way you can have any kind of backdoor it unless until you backdoor the whole golden image file in itself. So gaining access to kernel, it's good if you want to do a certain set of tasks. But however, from the information security point of view, at least from what we usually do, that is red teams, we are not a lot bothered about it, because the first thing is that the kernel is probably one of the most secure things in the Windows environment. The more you start reversing, you will realize that Windows does not have just one kernel. Microsoft has three separate kernels which run together at the same time, which sounds a bit weird, but yes, it has three entry points, and that resides within your NTOS kernel.exe itself, which is basically responsible for loading all the three different kernel based drivers directly into memory. One is basically for your hardware virtualization, one is for your Windows core, and the third one is basically for Linux. That's what the three different at least that's the at least the two one those two are that I know. That's basically the Linux one and the Windows core ones are correct. The one with the hardware virtualization, I'm still reversing on that to identify what it does. But uh, reversing your Windows systems via especially Windows kernel can be a bit of a pain. But yes, that's a quick overview. And most of the time, apart from reversing, you have you reversed the Windows kernel, by the way, Alex? The three kernels. Okay, cool. Then you know what I'm talking about. The yes, kernel exploit dev. Yeah, then you might know about what I'm explicitly saying over here. So yes, yeah, but I think I'll keep that topic apart for now because we have a lot of other people and we would still need to continue through the slide decks. But yeah, it's a good chat for another day maybe. So going back to thread internals, yes, for every process that gets created, it's type of like a thread for your kernel itself. The kernel stores various information about your processes that gets created into the memory of the system itself. All the threads share the same memory space. Fibers are a subset of thread. A lot of people, I think, do not know about fibers. Fibers are something like really interesting topic in itself, and they work extremely different as compared to threads. The nature is totally different. You can have multiple threads running together at the same point of time, but you cannot exactly do that within a single thread can only run one fiber at one point of time. It cannot run more than that. If you try to run more than one fiber, you will eventually be caught in a deadlock, and your process will stop working in that case. So, but fibers are a different thing altogether. We are not going to take a look at that. If required, I can take a look at that on day 4, but currently that's not a part of the TOC. Coming back, the thread environment block, according to Microsoft, the underscore TEB or your thread environment block structure looks like this. You have a lot of different structures in here, and most of the time you can rewrite or recreate the whole structure of TEB by just using WinDBG itself. So if you quickly go over here, this might be a recap for those of you who have already sat in my previous workshop, because we did cover a bit about reflective DLLs over there as well. So when you open up WinDBG quickly, uh, you can type dt nt exclamation underscore teb. Dt basically means display. In the zip file that I shared in the channel today, you could see that there are like various files over there, and you will also file a WinDBG cheat sheet over there. When you type DTNT exclamation TEB, you would see the exact structure of your thread environment block that you have. You can see the first part itself is a TIB. You have environment pointer, client ID. Client ID is basically your main process ID and your main thread ID, which gets attached over here in a hex format that gets stored, and a few other information and offsets of where these objects in the inside the specific structure lie into memory. So currently, sorry, my bad. So currently, what we are going to take a look at is how the TB works, how the PEB inside TEB works. We have process environment block, as you can see here. How both of these structures, or what both of these structures look like. Once you have a good amount of information on what both of these structures look like, you can actually walk through the TEB to find PEB. Inside PEB, you would find the Windows loader over here, and inside the Windows loader you will find all the structure which contains all the DLLs of Windows. Now this is important to know because this is what we will also be doing in our reflective DLL, and we will be using that reflective loader to load our C# code later on today. So it's important to understand how both of them work. So you can see inside PEB, we have LDR, that is of the format PEB LDR data. And this PEB LDR data is basically a structure which contains a doubly linked list. Doubly linked list is basically your nested structures that you have. One structure contains another structure for the next DLL, which contains another structure for the next DLL, till there are no DLLs left to enumerate. So you can also type DT exclamation underscore PEBLDR data. You can see the different structures here. A quick Google search of this specific API call that we have here, it tells us that this API call is, sorry, not the API call, my bad. A quick Google search of this structure will tell you that, okay, sorry, I'm in the, let me go to the Microsoft website itself, not over here. Yeah, let me just type list entry, and I think that should give me the direct link for the Microsoft website. I think I'll just, instead of going into list entry, let me just search for PEB LDR data. So if you go to the Microsoft website, Microsoft clearly states that this is of the data type LDR data table entry. That's what we have over here. And as you can see, in memory order module list and all the other lists that we have. So we are simply going to take a look at what this means by typecasting it to our LDR data table entry. So if you type the exact same thing over here, it should tell you the whole structure. We can see this structure contains we have the in-memory order links, which is of list entry, memory order links, initialization order links. These are nested structures for each structure that you see over here, every DLL. And the remaining portions are the information or the metadata of your DLL into memory, how it was loaded, when it was loaded, the DLL base, entry point, size of image, and everything. So if you are able to find out the DLL base, you should be able to find out the main main core of your specific or the H module of your DLL. Now, one more thing what most people don't know of is some of you might know about DLL base, some of you might know about the where did it go? The original base, but there are more than uh, these two ways to actually find the base address of your DLL. Now, I won't go into detail. I'll let you guys figure it out and I'll let you know before the end of the day. But we have over here an entry point. Now, this is an entry point. Most EDRs usually hook DLL base, and you should be able to use original base over here to find out the where the original base was loaded into memory if your DLL base was actually hooked. That's what Sentinel-1 does over here by hooking the DLL base. However, one thing that Sentinel-1 does not modify is the entry point. Same is the case with most other EDRs. If you are able to walk through this, instead of getting the DLL base, find the entry point. Now, if you remember, when you load a specific DLL into memory, let's say I will go to C Windows System 32 and let's say kernel 32.dll. Inside the optional header, you would find we have the address of entry point. Now, when this address is loaded into memory, if I go here and let's say I will load this up, in the logs directory, you should see kernel 32 loaded over here, as you can see. And this kernel 32, let me search over here. If I follow the entry point in disassembler, you can see the value here that is basically 070D0. Whereas you can see the same thing over here, 70D0, not the one though, but the 70D0. This means that wherever this DLL was loaded into memory, this value was added to the base address over here, which means that what you can do, if you find the entry point of the DLL into memory, because this is not hooked, most of the time only DLL base and your DLL base is hooked. Original base, I have never seen original base being hooked, but just in case you don't want to use either of these, you can also go and use entry point, which I haven't seen a single EDR hooking it till date. Once you find the entry point, you will have to perform a bit of an arithmetic calculation to switch back from over here, because this entry point will be your pointer that you see over here. But this is not the base address of P. If you just right click, follow it, let's say in dump over here, you can see that this is just one part of your whole P. And if you keep on scrolling, you will eventually reach the entry point or where basically your core actually starts. And this is where your kernel 32.dll was actually loaded into memory, which is also your base address, hopefully, as you can see here. So my point over here is that if you find this entry point and this entry point, and if you keep on subtracting -1, -1, -1 till you reach the MZ header or the NT header by going back, because if you see that currently you will be over here, which should be at the address over here somewhere, and you will be at the offset 110 from the start of your DLL. So if you keep on subtracting -1, -1 and keep on trying to find the NT header signature or the DOS header signature, you should be able to find the entry point for your P, not the entry point, the DLL base address, without even having to take a look at the DLL base or the original base in this case. So this is a totally different technique to actually find the entry point. And once you find the entry point, this way you can find the address for NTDLL or kernel 32. And once you find these, then later on, without calling any API call, you can actually walk through its EAT, call other EAT functions, which you don't have to worry about being initially hooked in this specific case. So does this make sense as to how the whole PE can be walked through to get the information? Yes. So if you go through the whole structures over here, right, you will realize that there are several other interesting things. I won't go into all of these in detail, but it's a pretty interesting thing as you if you go through each of these. You also have something called as a base name hash value, which is one of the unique hashing technique that Microsoft uses. Most of the time, we usually end up using RAW or RAW13 to extract this hash. But if you're able to use the Microsoft's own hashing technique, which is X65599, if you're able to use that X65599 technique to extract this hash, you can literally loop through the entry table without even having to perform any string comparison for your base DLL name or full DLL name in this case. However, currently we will not be going into the base hashing. That will be again a different task altogether. Currently, we are going to loop through this and identify wherever DLL resides in memory. So what we can do is we can just type exclamation PEB. This gives us all the current pointers for our process environment block in memory. Your process environment block contains several metadata about your DLLs that have been loaded. The PEB is always at the offset at 0x60 in the GS segment, the GS register, which is your general segment register. And that will always be there. That's as per the Microsoft documentation. In case of x86, it is always going to be at 0x30. That is the offset for x86. Since we know this, what we can do in our code is basically we can try to find out the GS registers 0x60 offset. We get the pointer to PEB. Inside PEB, if we scroll to the very top, sorry, this is TEB. Inside PEB, you can see that we at the offset 0x18 we have LDR or LDR PEB LDR data. That is this is the name. This is the structure format. And according to the PEB command over here, what we have, as you can see, is that this specifies that this is the pointer to our LDR structure. So we'll type NT exclamation underscore PEBLDR data, and then we'll simply specify this value. Now this structure will be typecasted to this pointer, and whatever resides starting from this pointer will be printed to us on our screen over here. As you can see, the whole information. These are the different pointers for where your in-memory order module list and other information lie in memory. And you can see our in-memory order module list lies in the offset 0x20. So I will take this up. I will type LDR underscore data table entry, because we saw earlier that all these entries, these three entries are of data type PBS data table entry over here. So we'll take that and we will extract this value, copy it and paste it over here. Now you can see all the information over here for our PE in memory. You can see the in-memory order module link, the base address over here of the DLL, the DLL entry point. Now this address that you see, there is currently an offset and not exactly a base address. Though you can only see the base address when you are actually running it in memory. The size of the image, the PE, the file name, and so on. Similarly, you can actually go to the next slot. You can see we have the next in-memory order module links here. You can actually go over here or basically extract the next value directly from over here as well. If I copy and paste this, this is going to be cmd.exe. As you can see, I can extract the next value here. The next value should be entry_dll.dll, as you can see over here, and the next value should be kernel 32 and so on, which means as we proceed through the different pieces of code, you will be able to find the values. And you can see right now the DLL base and the entry point. You can also see the entry point 70D0, which if you subtract directly the actual entry point, or if you keep on doing -1 over here, you will eventually reach the MZ header. For ntdll.dll, let me see. Oh, nice, interesting. So in this case, I think what you could still do is you could still try to find the address for kernel 32, which I think kernel 32 is still there. And once you find the address for kernel 32, you can extract the different functions, and there are several functions using which you can still go through them. Or one more thing that you could do is find the entry point of kernel 32 I will cover something called as vectored exception handler day after tomorrow, and I will show you that once you find the entry point, how you can walk through, find the DLL base of kernel 32. Once you find the DLL base, walk through the P of kernel 32 like this. Go to the export directory, find the find your add vectored exception handler API call over here, and once you find that, you can literally try to use the add vectored exception handler to add maybe a breakpoint or maybe a page break directly to find the address for your NTDLL. So all of these can be done. The core aim here is to find at least either NTDLL or kernel 32, either of them. Yes, I will explain what -1 I am referring to. So currently you can see over here that this value that you have over here that you see is basically 7FF9FF6070D0. Now the reason why you're seeing this value is because this is the DLL base where the DLL gets loaded. If you add the entry point that you see over here 170D0 to this DLL base, you will get the base address of the entry point. Now, think of it in this way. Create a while true loop. Continuously, in that while true loop, perform a -1 operation on this value till you, and you keep on doing that. So basically, for example, you take this value. Let me open up, let's say, this value here. We have this value that is going to be our entry point, and we have the first value that is going to be DLL base over here, as you can see. So what we are going to do is that this plus our entry point 1070 basically becomes our entry point that we have over here. So now what we are going to do in this case is that we will run something like, for example, maybe a while true loop that we have. Inside this while true loop, let's say this value is under, let's say, for example, void, let's say, entry ptr equals to this, let's say. Now what we can do here is we can just simply type entry point minus minus, which means we are going to subtract -1 from here because we are now ahead of the original base address that we have, and then we will typecast whatever value we have after performing a -1 instruction to maybe something like, for example, nt image header structure. We'll typecast this value that we have, and we'll try to extract and see whether when we typecast it, whether the start of our nt header is equal to 0x4050, and we will also typecast it to the DOS header that we have over here to see whether the DOS header is equal to 5A4D. So we will keep on doing minus minus, and this will only, this value that you have, this will only be true when we reach this specific location, similar to what your reflective DLLs also do in the backend. So if you do something like this, for example, if this value, if this returns true, it simply means that you have found your base address, and entry ptr is going to be your base address after that. Does that make sense? Is it clear, or any doubts? Okay. So I'll show you how this can be done. Instead, in fact, Stephen Field's reflective DLL does something similar to this, not to find the entry point, however, but to find the base address of the reflective DLL in memory. So we are going to use that technique along with our entry point value that we have found here. So going back to our debugger, yeah. So this is what we are going to do inside our core as well. And a quick example over here. Let me go back to the slide decks. You can see PEB LDR data, the offsets over here, and the whole autopsy as to how it looks like in memory. So this is the whole summary of what we were actually trying to do. Find the address of TIB, find the GS and the FS segment register for x86, GS for x64. Find the address of PEB 0x60 for 64 and 0x30 for 86. Find the address of LDR data table entry. Find the first value will always be the process itself, which in our case was CMD. The second value was NTDLL, and the third value that we had was kernel 32, and then we can go on from here on out. So any doubts onto this specific part, how the PEB or the PBLDR data table entry works. No doubts, no questions. Okay. Uh, I'll do one thing. I'll give you guys around 30 minutes, and your aim over here is to go through this piece of code, and whatever pseudocode I wrote over here, your aim is to convert this pseudocode and convert into an actual code to find out the base address for kernel 32 from its entry point. That is basically going to be the task over here. So is that clear? If unable to do it in the next 30 minutes, I'll give you the sample code of how this can be done. But is it clear how the actual value can be extracted? And for those of you, there is a GitHub repository that I have created. Uh, I think it's open for everyone. So from over there, you should be able to get some help. So you can just go through this code. I've just shared it over here. In the get and the address hunter.h repository, if you scroll down, you should be able to see the PB and the LDR data table entry, all these structures alongside how to find kernel 32. But make note that this example of finding kernel 32 in memory, it utilizes DLL base. We don't want DLL base because DLL base can be hooked in the PEB. So we are going to extract. So when we reach this value, instead of finding the DLL base, our aim is to find out the entry point, and using this entry point, you can loop back like this to find out the DLL base. Is this clear? What needs to be done? Any doubts on this? Okay, so I'll quickly start a timer for 30 minutes. In case you have any doubts, feel free to ping me up and yeah, let me know. Yes, of course. You can take a look at over here, or what you can do is, yeah, I've shared you a sample repository called as Reflective DLL. That's basically a replica of Stephen Fewer's Reflective DLL. If you open that code, you should find somewhat a code which should be somewhat similar to this. If you go to the reflective loader code, you would find a somewhat similar code over here. This should probably help you out as well, which is exactly what we are trying to do. Except that in that case, he's not the Stephen was trying to find the address for the base address of this reflective DLL, but the core logic is the same. I will keep this timer over here. Has anyone completed, or anyone is stuck? Do let me know if you're stuck or if it has been completed. So anyone else who was able to complete the task apart from Alex? Lenny, Scott, Adebayo. Do you guys need more time, or are you guys still doing it, or may I know the status? Oh yeah, hi. I forgot Dwayne was also there over here. You completed Dwayne? I think you should have completed that by now. Cool. Let me share the code here quickly. It's a pretty small piece of code, just a single C file. So I'll just share the C file itself onto the chats. I posted that onto Discord channel, a file called as entry base, and this is what the file looks like. So I haven't seen any EDRs trying to detect this, like literally zero EDRs. And when I say that, I mean that because I have reversed a ton of EDRs, and I haven't seen anyone hooking the process, the entry point of a DLL. So this is as simple as it gets. You have int main, you have find kernel 32 entry point, which goes over here. You read the 0x60 offset. You extract the handle over here for your PEB. 0x18, if you remember, this is the LDR data table entry over here. Then we have 0x10, which is your in order memory links that we had. We are going to get the first pointer, the second pointer. So the first pointer, this is going to be of your current process itself. In my case, this process will be entry to base.exe. This will be the pointer for that specific structure. This one will basically be for your ntdll.dll, and this one is your kernel 32. Now inside kernel 32, you can see that we are extracting the offset 38, and which if you take a look at this over here, you can see the offset 38 that we have is the entry point. So if we go back, you can see this is going to be our entry point that we have at this specific offset. We extract that, we return it to the user. Once we get that, we will print it to screen the offset. We will start a while true loop. We will check whether the entry when we timecast into p image DOS header. So p image DOS header is a pointer to a DOS header structure, and the values that you see here are the exact same as to what you would see in the DOS header here. You can see eMagic, CBLP, CP, CRLC, and all those things till we reach alpha new. And your alpha new that you have over here, ELFA NEW, this is always going to be the offset for your NT headers. So if you take a look, we have starting from 0 till 3C. 3C says that the offset to NT header is going to be 0xE8. If you go to the E8 offset, you would see the address over here, that is 4550, which is nothing but short for your NT header that you have. That's your PE value in memory. So we are doing exactly this. We are extracting the NT header value, that is this value that you see. Once we extract that, we're going to see whether that value is greater than the whole size of image DOS header, the whole size from 6 till 3C, whether it is greater than that. If it is greater than or equal to that, and if it is lower than 1024, because this value should not exceed the 1024 bytes, the first 1024 bytes, because the P section that you have, the initial DOS section and the NT header, they will always be lower than the initial entry point section that you will be having. So that is the reason why we are just going to check whether it is lower than 1024. If it is, then we will add the header value that we have, that is this offset that we extracted, with the base address of our DLL. That is going to be our actual value. Once we get this value, we are going to typecast it to NT header, that we have this, and we're going to verify whether if we typecast and extract the signature value, whether we get NT header, NT signature value. That is basically 0x
00004550. That stands for PE in memory, as you can see over here, which is exactly what we have. So in short, what we are simply doing here is since we have reached this specific, sorry, one second, this specific value in memory, the base address, we will subtract it by 1111, and we'll keep on doing that until we reach this value. Now we don't know whether we have reached this value, so we are going to typecast it to a structure, validate whether we have received this value. We will also, just to make sure that we have not reached any other string called as mz in memory, we will also extract the empty header, try to typecast the empty header that we have with the to the base address we extracted, and we are going to verify whether typecasting after it, whether it resolves to n to your PE header over here. So if our value of PE header and our DOS header are matching, if both of them match, it simply means that we have finally reached our entry point. As you can see here, a while true loop, check if we have reached a DOS header. If it have reached a DOS header, that means it is basically the entry point that we have. But this can also be a false positive, and for the same reason, we try to extract the NT header offset. We get the NT header's base address. We typecast and check whether we have received it. So if both of these two match, it means our entry point is what we have reached right now, and we'll keep on subtracting if we have not reached. Now, if you run this, you can compile this whole code into your assembly as sorry, not assembly, my bad, Visual Studio as well. For the time being, I'm just going to compile this over here with my GCC. So this is MinWGC that I have over here on my Linux system, entrybase.c, and my file over here in my documents directory. So if I go back and if I should find k.exe, and you can see it tells us the entry point and the base header. You can validate that by simply adding maybe a get char over here. So I will just type, let's say, get char so that it blocks the exit. We will just hit it over here, try to run this again, and we can maybe open our debugger or either or your process hacker, either of one that you require. Just search for find a.exe, and if you go to the module section, you should see the kernel 32, that is 9ff5f0000 that you have over here. Does that make sense? Any doubts on this? Any questions? How the extraction of kernel 32 work? Why do you think to compare the value of for MZ? 4 5 your this is basically the short. This is M and this is Z. MZ. That's the reason. This is the ASCII value for M and Z. No, not really. So this value that you see over here, if you click on this, you would see that this is usually something like, for example, MZ00. That's basically the value is over here. Sorry, I don't think I quite understand the question then. Said, yes, the compilation code for Linux. One sec, I will share it. Give me a sec. Copy and paste it. Okay, coming back to the question, to avoid comparison, LDR, get starting the LDR module data table entry. Okay, what do you think to compare the value? 90, it does not start with 90, right? Or am I wrong? Does it contain? Ah, okay. Yeah, yeah, the okay, I understood right now. Sorry, my bad. Yeah, you can also compare it with this. Not an issue with that. I am not 100% sure. I haven't tested this out, so I just saw the word value over here that you can simply compare it with a double word in this specific case. That is 00905A4D in this specific case, and again, I mean, yeah, it might work well. The only concern that I had is that if in the whole code, if let's say starting from your, it might not be, I don't think that should be an issue, But normally, if you have any other string in memory from between the offset 110 to the offset 0, if you have something similar to this, then you might end up having an incorrect value in that case. If the DL base in the PEB is different, that means the DL has been. Yes, you are correct. So if you take a look at, I posted a tweet in January where I was reversing Sentinel-1 and I posted it that I was able to find the incorrect DLL base. And so what EDRs like Sentinel-1 does is that they will add a fake value. That when I say a fake value, it doesn't mean it's a fake memory address. It is a valid memory address, but it is not the actual DLL base of your PE. But what is more funny is that when you walk through the PE, right? Let me go back to this specific code. When you walk through this LDR data table entry, what these EDRs will do, or some of the EDRs, is that they will change this code with a custom code or a custom memory region. Maybe something like, for example, if you have, let me just copy this. Let's assume that if this is going to be your original region, then your actual value over here, instead of this, what the EDR will do, it will go ahead and convert this to maybe something like, for example, 140000. Now, this region that you have, this will be a valid region in memory that was allocated by your EDR by calling virtual alloc in this specific case. Virtual alloc or NT-protect virtual memory, whatever the EDR is going to use. And what the EDR does is that the EDR, before you can actually parse through and walk it, the EDR will replace the original value that you have with a custom value. And this custom value that you have, it will actually contain the kernel 32, but the name would be different over here. It will be something like kern132.dll. That's what I have seen at least. And this region will also be backed in memory over here. You will also, if you go ahead and search this value, you will actually find a DLL in this which was manually mapped by the EDR. So what happens over here is that when you find something like this, in your case, if you're not validating whether your DLL base is right or you're trying to use any custom technique, then you will eventually end up into this region and will start walking through this DLL base region to find the EAT, that is export address table, import address table, and so on. What you're eventually doing is that you don't even know, but you're eventually walking the fake DLL's address loaded by the EDR in memory, and this is a valid section except the fact that there is no .text section, which means whatever EAT you are passing and you are trying to call, all of those EAT sections eventually belong to a section into Sentinel-1 or your EDR's memory itself. And that section, so what the EDR will know which functions you are going to call and what you're exactly going to do. But the address over here will be the custom memory region and not the actual region. Does that make sense? Or is it too, or I was too complicated in explaining this? I think it was a bit too complicated. Yes, sure. So, Tudor, I'll share the code for Visual Studio. Don't worry, I'll share it in a sec. Uh, okay, so let me repeat everything that I said over here again. So when you walk the P, right, your aim over here is to find, let's say, either a syscall in memory. In order to find a syscall, you will need to find the NT API, for which you will need to first find the either directly the NT API call, or you will need to find the Windows API call in kernel 32. Let's assume that you're going to call the Windows API itself or the NT API, either of them. For both of them, you would have to call get proc address, but get or proc address will only work when you actually know the function address for get proc address or your base address. Now, for the same reason, you can call get module handle or load library, but most of them are usually hooked by default. And even if they're not hooked you by default, don't know the addresses for them. The only way to extract these into memory is by walking the P over here itself. Now, when you walk through the PEB of the PE, you will see that the second DLL is most of the time NTDLL.dll, the third DLL is kernel 32. So what happens over here is that now EDRs, some EDRs usually know that most of the code that you write, they will either be Cobalt Strike or maybe the loader that you're using from Metasploit. Now, what happens in this case is that they will modify this DLL base because they know that most open source or known C2s will use this technique. So they will try to hook DLL base. Now, in this scenario, what you can do is if you actually try to extract this value, which should be the legitimate value, but they are not anymore. So what happens is that when you try to extract this value, you will eventually end up extracting some other value because the EDR will replace this memory region with a custom allocated memory region. So when you try to extract this value from memory, you are actually extracting this value from memory. And when you think that you're walking, when your let's say Cobalt Strike loader or anything else is trying to walk this DLL base to find out the EAT and other stuff, you are eventually walking the address of this region to find out the EAT. And since you are walking that, and eventually when you call it, by default, your EDRs will add a page guard to this specific region. And this page guard, the moment you go ahead and try to access it or even read any specific EAT region, it will basically call the, it will basically hit the page guard. And if you're not handling the page guard's exception, it will eventually lead to a crash. So it will either crash or it will basically be, or the crash will be handled by Sentinel one's DLL into memory, which also uses add vectored exception handler API call to capture the specific exception in this specific, to capture the exception for page guard. So now, since you cannot extract the DLL based region, the only two options that you have left is to get the address from over here, the original base, which also contains your original address for your DLL into memory, or by extracting the entry point. However, there is a catch to extracting the original base. What happens over here is that when you try to extract original base, this will work for Windows 10. Yes, I haven't seen a single EDR hooking this specific region, but this whole LDR data table entry structure that you see, this is different for Windows 8. This is different for Windows 7, which means there are a few values. I don't recall which one. I believe telemetry entry process is one of them. And there are a few other values which do not exist in Windows 7, which means all your offsets that you have, the original base, it won't be over here. It will be somewhere over here or maybe here, and it will be different into every other, into Windows 7, Windows 8, and Windows 10. Maybe it will change again in Windows 11 later on as well. Which means if you directly try to extract the offset, which is at a very later stage into the memory region, you won't get this specific structures object, and it would end up in a crash in anything apart from Windows 10. If you want to run it in Windows 7, then you will have to again go through the whole region. You have to create a different structure for Windows 7 into memory and then try to extract this value, which will work. But in order for that, you will either need to create a separate payload, and you need to know firsthand that you're going to target Windows 7. You cannot create a payload that is totally dynamic in this case. So in such scenario, what you can simply do is you can extract the entry point over here, because this is the same starting from Windows XP till date. And since this is the same, you won't have to worry about this value being different. So just extract the entry point, walk through it, and try to find out your actual region that you have. Does this make sense? The whole logic behind the three unique techniques? Cool. And coming back to, I think, Tudor's question, the code is not working. So this code that I wrote, I am actually Linux user, so I quickly wrote it in Linux over here. Let me just copy and see if I can quickly make this run in Visual Studio. Create a new project. It should work. I don't see any reason why it should not work. But again, I don't trust Visual Studio. Never been a fan of it. Day2, yeah, I'll just save it over here. Select folder, get kernel entry, kernel entry, create. Yeah, I mean, I know a lot of people over here will probably start abusing me because I am not a fan of Visual Studio. I always like to develop my tools in MingW. Main reason that I am a Linux user and not a Windows user. That's the reason. So, and yes, I don't think that should be an issue until unless something messes it up. It compiled. Were you getting a compiler issue? Studio is a nightmare. It works it acts extremely stupid at times. I think even Scott faced an issue yesterday, and I think Tudor, you said it was not compiling. Did you face this issue over here, or is it not working at all? Let me check whether it's working or not. Yes, VS Visual Studio doesn't like shortcuts. That is absolutely correct. Make sure it's not C++. Visual Studio is not at all flexible. Ah, okay. Okay. So you can see that it does work over here. Make sure you always change this to compiler. One more thing to keep in mind, I have faced issues when I started developing my brute rattle. I did face issues where I was initially compiling in debug mode. So in debug mode, it ended up crashing, but it worked perfectly fine in release mode. Now I did not have the patience or time at that point of time to debug through the debug mode, but it was pretty stupid, and that's why I decided to just stop building debug releases. I always directly compile it in release mode and start up a debugger, and I stopped using Visual Studio as well. So yes, that's my 2 cents over here. Okay, any doubts, any queries on what we have done till here? Any questions, any queries? No questions. Okay, cool. So we will go on to the next part that will be understanding DLL into memory. So your DLLs are supposed to be external code and functions, and they basically have imports as well as exports, unlike Ps which only have imports. However, there are some PEs which have import as well as export, especially when you talk about EXEs like NTOS kernel.exe, which have both of them. All DLLs have a DLL main entry point, and all of them are compiled as a shared library, unlike a P, which is not compiled as a shared library. Now, there's a major difference between the two. When you compile it as a shared library, it means it will have a different address on disk and in memory, which is basically what we call as a relative base address. But when you compile a P directly, or maybe an exe as a non-shared file, it will only be valid as it is on disk. You cannot load it into memory and run. If you go through some of the Windows P files or executable files, you will not be able to load all the exes into memory, whatever using the process hollowing technique that is currently there. Because some exes are compiled as shared in Windows, whereas some exes are actually compiled to be only run from disk and not from memory. That's altogether a different case, however, and currently we are focused more on just the DLL front. So we will just take a look at how this specific technique or the reflective DLLs actually work in memory. So load library, the reason why we're not calling load library is because load library only reads a P from disk, extracts its headers and everything, and typecasts it, finds the P entry point, finds the execution entry point, and executes it. We're going to do the exact same thing, but from a buffer that is currently into memory. There are different types of DLL linking, static, dynamic, and runtime. Depending upon what you have compiled, you may or may not have IIT sections. If you compile it as a static or dynamic, you will have IIT tables. IIT, sorry, not IIT tables. It should just be IIT, because IIT is short for import address tables, which is what you see over here. The DLLs which you have imported and the different Ps that you have, or the different functions that you have called from each of these import addresses tables over here. If you are calling, if you whatever functions that you're going to export, you will find these over here. So whenever you dump a P into memory, sorry, P from memory, you will find at least one export over here. Or maybe there could also be scenarios when you can just use the CF Explorer to erase the PE section directly over here. Now I will close it and not save it because I just mistakenly modified the kernel 32's export. So let me just I don't want my whole system to crash because of that. So let me go and yeah, it's back again. My bad. So you can also go ahead and erase that in case of your reflective DLL if required. However, in our case, what we are going to do is we are simply going to create a reflective DLL, see how it works in memory, and we are going to use that reflective DLL for our C# as well as our PowerShell code. Remember that we are not thinking about evasions right now. There are several ways with which you can actually evade the whole reflective DLL into memory. Currently, we are not going to focus on the evasion part because that's specific to the MOS workshop. So right now, we are just going to extract the DLL, DLL's information from memory, and call its entry point, or that's DLL main, the entry point that we are going to call. So this is a simple example of how loading libraries at runtime look like. You take a function, let's say you want to call get computer name A. You create a type def for it. You can see the exact same methodology over here, except that we have created a function pointer, unlike our function. We load the library, we get the address for that specific function pointer in our library. We verify it's not invalid, and then we simply call the typecasted pointer that we have. It is as simple as that. Now, before we get a bit deeper into this, let's understand structures. Now, there are two different types of structures in memory. One, which is basically in the byte order into memory, and the other structure, which is normally adjusted. Now, one of the things that I always, I would say, hated about Visual Studio is its optimizations. No matter what you do, I mean, or maybe I am just bad at Visual Studio, I don't know. But no matter what I did, I was never able to disable the optimization completely. However, there are options to pause some portions, and that's again altogether a different headache. So, in short, by default, let me show you an example. Let me go back here and let me go to File, Open Project Solution, Day 2, and let me open this struct enum solution that we have here. So this is a very quick example as to why this is important. Now let me erase or let me delete the pragma comments here, and I'll explain why I'm doing that in a sec. I will compile this small piece of code. It's a very small and simple piece of code. We have a unsigned car buffer. It just contains garbage values, hex values starting from 1, 1, 1, 2, 1, 3, 1, 4 till 37. Just garbage value starting from 1 till from 11 till 37 hex values. We have a very simple structure which contains different values. Word, that's basically of 2 bytes. D word, which is of 4 byte. Q word, which is of 8 byte. Byte, which is of a single byte. An 8 byte array that we have, and that's all. We'll create a structure from this structure that we have. That's a sample. We have created an empty structure and initialized it with zeros. We'll print the size of each of these values over here. You can see the size of the whole structure. The size of the value is, so this should give us like 2, 4, 8, 1, and 8 over here again. Then we are going to typecast our pbuff value that we have over here, and we are going to typecast that directly to psample and move that inside a psample is basically a pointer to the sample structure that we have. And we are going to move the basically create specify this is the pointer for psample into our new variable psample2, my sample2. Now we'll try to print each of these values. Now I have a question over here. When I try to print these values, right? Let's say I try to print the first value A. What is the value that I will get over here when I try to print A? What should be the value here? Any guesses? Anyone? I've typecasted this pbuff structure to psample because this is a pointer into memory, this is a pointer into memory. So when I try to extract the word value, what should I get from this specific structure? 0x1112, correct. What should be the second value, that is B here? Okay, that's a good answer. So two different answers from two different people. 1112 and 1211, and then it should be 13141516, or maybe in reverse over here. Now this is where Visual Studio makes things very interesting. Let me build it and show you the difference between them. Yeah, let me just clean and build it because I am too lazy to find out the path over here. Yeah, found it. And let me run this. Let's see what do we get. Okay, let me kill this because we don't need the debugger here. Okay, perfect. So you can see the first value that we get is 1211, that is in reverse order. Then the second value we have is 18171615. Any guesses why it is that? Why did it directly go over here 18171615? Where did 03 and 014 go? Exactly, padding. So Visual Studio by default adds padding for its optimization whenever it compiles it. Now, the only way to avoid that padding is using something like this. It shifts everything by a word. That is correct. So in this scenario, what we are going to do is there would be scenarios, and this is extremely helpful. I'll tell you where. When you're dealing with PEs into memory, or when you're dealing with, let's say, when you try to write something of your own, like for example, a Kerberos encoded ticket, for example. When you try to extract a Kerberos encoded ticket from memory, those bytes into memory, or the network bytes, whatever network values that you get from a packet, those bytes do not have such paddings. They will be exactly next to each other. So if you don't use something like pragma pack or pragma pop over here, you will end up getting incorrect values over here in the end, which is not something that you want. So you basically pack all of them together so that we don't have any padding. We will compile it, and let's see what we get back here again. You can see the whole output changed over here. You can see the sample over here, the value also changed. And this is exactly how it should have been, which is what MingW by default does. So if you take a look at this, this is going to be of around 2 bytes. We have over here as 4, that becomes 6. Over here, this becomes 8 over here, that becomes 14. This is basically 15, 1 byte, and then we have this, which becomes 23 in total. So if you add them up, the total size is 23, which is what you see over here when we pragma pop and pragma push. The value over here, the remaining values are going to be the same as you see here, including this. And when you typecast it, you will get everything in a proper order. Unlike earlier, where you saw 1, 1, 1, 2, then 5, 6, 15, 16, 17, 18 instead of 13 and 14. Right now, we have basically removed the padding, and we have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, and so on. So the reason I'm showing you this is because we are going to do the exact same thing to our reflective DLL into memory to extract information from there. Does this make sense? Is this clear how the structuring works for padded and not padded structures in memory? Or is it too complicated? Okay, it's clear. Got it. So let's go back and see how what we can do for our PE into memory over here. We're going to do the exact same thing for our reflective DLL. It's not really fancy. Let's assume that this is going to be our reflective DLL that we have. So what we're simply going to do is we're going to go to the DOS header. You can see that the first value is word. And if you perform a quick Google search over here, you should also get the same. Microsoft has a really good documentation on PE format. And if you go to the documentation itself, it should tell you what is the size and specification for each of these values you have. You can see the first value inside, sorry, not over here. Yeah, you can see that the stub over here will always start at 0x3c for your P header. Once the P signature starts, it will then have your COF header, which contains your machine information, and each of these are the offsets for and the size for each of the values. Exactly similar to what we have over here. You can see the DOS header at 0x3c. We have the P signature, which is what you see over here, 0x3c. You have the P signature with PE over here. As you can see, E8. At E8, we have P and E00. After that, we have the file header, or more like our common object file format, COF header. And you can see this is the word value. This is again of data type word, D word, which is 4 bytes, D word, and so on. And if you keep on continuing, you will see byte, word, D word, eventually before reaching the dot text section that you have. And over here, again, the first values are always of 8 bytes. And the remaining values that you see are basically D word and word again. So in short, you can see that at zeroth offset, we have 0, 2, 4, 6, 8, and so on. So whatever these values are there, that gets added to calculate the next address that we have, or the next offset into memory. So we are going to loop through this. Our aim here is to reach here, find the export directory RVA that we have. So let's assume that we have our EDRA, RVA. RVA is your relative virtual address into memory, and our address that we have is 99080. Now our aim here is to convert this relative virtual address that we have and to find out where exactly it resides in memory. In order to find that, we'll have to convert this RVA to file offset. Without finding that, we cannot extract that. So what we can do in this specific case is we will take this 99080 and we will see where this value 99080 resides in the dot section header. And you can see that if you keep on adding 2, 4, 6, 8 over here in the offset section, you will eventually reach over here in the file header. In the file header, when you reach this specific section, let me extract this and open a calculator here. When you reach this specific section, you see that the size of optional header at FC specifies that the total size of this header is going to be 00F0. So if you take this offset, which is FC plus F0 plus 2 bytes for this word value, because this offset of optional header starts from this, but we also have the characteristics in between, which is of 2 byte. So if we add 2 bytes over here, we get 1 double E. That is the offset for our, as you can see, it is basically the size of optional header. So after optional header, we have the section header, and you can see our initial value over here starts with 1F00. One sec, I think I missed out something. FC plus we have, yeah, sorry, it should be 4 bytes, not 2 bytes, because this itself is of 2 bytes and this is also of 2 bytes, so both of them become 4. So FC plus 2 bytes over here plus 2 byte for this value plus the offset is of 00F0, that is the whole size of optional header. So F0 becomes 1F0, which is also the start of our, as you can see, the section header. So now once we have reached the section header, we can, I'll just write it down, that section header starts at 1F0, F0 that we have. That is basically this specific section that we have, that's the offset. And this is going to be the file offset, remember that. We don't know what is the file offset of this, which is what we need to find. So what we will do is, we will take this inside a data directory, because once we keep on adding the offsets, instead of adding, let's say 00F0, if to FC, if you add, let's say 2 bytes, you reach here, FE plus 2 bytes, you will reach over here, and if you keep on adding that, you will eventually reach this specific section. Once we reach this specific section, we take this value 99080 and we try to see in which section does it explicitly reside. So if you take a look at this over here, we have our first .text section that starts from 1000 and from the offset 1000, or not the offset, more like the relative virtual address, and it ends at 7400. But our value 99080 does not reside between them, which means our RVA is not over here between these two values. Let's take a look at the next value that we have over here. The next value that we have is basically the .r data section. Our R data section that we have over here is basically going to extract the our R data value that we have. This value starts over here. This is the total size of this specific. So if you add them, let's see what we have. We have the first section is 1000 plus 70400 over here, which is less than our 99080. So we will not do anything over here. The next value starts from 7F000 plus we have the total size of this section is 33000 that we have. You can see we have the value as B2000. And if you take a look at this 99080 resides between 7F000 and B2000, because it is less than B2000, but it is greater than this value, which means our value resides in this specific section. So what we are going to do is, since we find out that this resides, sorry, my bad, between 7F000 and 33, and basically this should basically be an addition, plus 000, which simply means that since our RVA is over here, we will perform a simple arithmetic calculation with the help of which we will get the file offset. This arithmetic calculation is actually mentioned into the uh, sorry, it's actually mentioned over here into the P format region. If you scroll down, it's a pretty large place, so you will have to search it up over here. But in short, the actual calculation over here is that if you find out the file offset, you'll have to take the RVA that you have, subtract the virtual address that you have, and you will simply get the file offset after this. So what we are going to do is, and sorry, you will also have to add the total address of the region, the base address that we have. In our specific case, this is going to be the raw address that you see over here. So let's see what we get over here. We have our virtual address. So we will take 99080, that's our RVA, minus our virtual address. Our virtual address over here is going to be 7F000 plus the raw address size that we have over here. That's what we are going to add it to, plus this value. And let's see what we get over here. If we add this, this should be the offset that we require. 99080 minus 7F000 plus 7D800. You can see we get the value as A1880. Now let's see and validate whether this is correct. We can go to address converter here, take this value, convert it, and see. Okay, so I think I might have calculated something incorrectly. One sec. Sorry, I think I have to subtract this by sorry, my bad. Not this raw address. I have to subtract this value. My bad. Let me just go back. Should be plus this minus 33000. One sec. 99080 minus 7F000 plus 33000. No, I think even that is wrong. One sec. Let me just search the, I don't recall the exact calculation over here. Virtual address. Yeah, should be somewhere over here. I made a mistake in the calculator. One sec, let me see. 7, okay. 99080 minus 7F000 plus 33000. No, I did not. Or did I miss something? One second. Subtract the virtual address and add the one sec. Sorry, we have to add the, sorry, my bad. We have to add the base address over here. So one second, 99080 minus 7F000. We get this value as 1A080. And this should be plus the raw address, I think, 7D800. Yeah, sorry, my bad. It was the correct one earlier itself. Yeah. So initially I typed that, my mistakenly I moved it, and it was a mistake in the calculator. And you can see that it's 97880, which is what you see over here as well. So if you just copy and paste this over here, my bad, the extra space, we can see it is the exact same value, which is going to be our offset. So if you go back over here and if you take a look at this specific offset, we can see that our value in the EAT export address directory basically contains the offset 97880 over here. And once you get that, again, this characteristic is of 4 bytes. Then we have another 4 bytes of dword, 2 bytes of word, and so on until we reach the number of functions that we have, the address of functions, and we have to do the exact same thing for this address of function as well. We will see where this address of function lies. This basically contains our executable region for our first value, the file offset. So we'll take this address of sections. We can see that this is somewhat similar to our 99080 section over here itself, which means that this value should be the same for the subtraction and addition. So let's see what we get here. 990A8 minus 7F000 plus 7D800, which brings us to 9789788A8. Now let's see what this value is over here, just so that we can confirm it. Address converter, and you can see that we have reached to 978A8. which you can see a 0, 1, 2, 3, 4, 5, 6, 7, and 8. And over here, you can see our actual region. The value that we get over here is 970090, the value that we have in specific to hex. And that should also be the executable region for our address that you can see 978A8 that we extracted. And this is basically where our first section lies. And you can see that if you loop through the number of sections that we have, you will be able to find all the other regions. But currently we are not going to pass kernel 32. We are just our aim over here is just to extract the first address that is going to be a reflective address and execute that. And that's what we are going to do in this specific code. So project open solution, if I go to so this is going to be reflective DLL, I think. Let me open this code. Yes, this code from Stephen Fewer does exactly that. As you can see over here, we open the a specific DLL which is currently on disk. We can actually embed this whole DLL into memory of this by using an XXD command on it, which basically dumps the hex values. Take that value, add that to the buffer over here, maybe into a header file or something like that. Read that buffer into memory, allocate the space, read the size, allocate buffer required as per the size, read the file into memory LP buffer. Now, since we have this in memory, we are going to take an address provided by the user in which we are going to inject it. Going to open a handle, create a process as per the name of the process that was given to us. If it's a PID, it will open a handle. If it's not a PID, it will create a process over there. Now, once it has been created, we will call get reflective loader offset. Get reflective loader offset simply takes your buffer. We can see it is basically typecasting to an unsigned integer pointer, which is nothing but your long integer pointer for your if the size is more than 4 bytes as well, it will still take it up for your x64 register. Now, instead of calculating all of these manually like we did over here, in this case, we are just typecasting it over here, our base address that we have. We are going to extract the export directory address, and similarly, we keep on doing that. Now, this offset over here is similar to what we just saw in a few minutes ago in our struct enum code, where we basically typecasted our buffer to a specific structure and extracted these values. Similar to this over here, in case of Stephen Fewer, he is trying to compare whether the exported function name is reflective loader. And he has done that is because in case of Stephen Fewer's loader, he is expecting that you might have one or more than one specific functions over here. Most of the time, you won't require more than one function unless until you want to hide one of your functions under hundreds of different functions just to make it look complicated for the reverse engineer to understand it. But in our case, normally you won't require this. You can get whatever first value you get and directly convert them. In our case, currently we are just doing this because reflective loader is going to be the entry point. We have our RVA to offset that we're converting, and this RVA to offset does exactly what we did over here. It takes the base address and the RVA, extracts the pointer to the raw data that we saw over here, our pointer to the raw data that we had, which Alex just told me about, and the mistaken size over here that I took was basically the raw size instead of the raw address. Sorry, yeah, the raw size instead of the raw address. Over here, that's what you should not take. This should be the correct value, which is what it is also taking up over here. Pointer to the raw data, which is your raw address. It tries to find out, it's going to do the same thing, RVA minus virtual address plus pointer to the raw data. RVA minus virtual address plus pointer to the raw data, you get the file offset. And finally, it will simply return the file offset if it is valid. Once we get the file offset over here, we will return the file offset directly to our code over here. Now we'll allocate some memory, we'll extract this, print this value, our file offset on the screen, allocate some memory as RWX region, copy our reflective buffer over there, create a remote thread, but the remote thread will be created after adding the offset to our library buffer. Now this is similar to what we saw earlier when we saw our entry point over here. This is basically the offset for our .text section. We added this to our base address to get the base address of our entry point, if you remember. We are going to do the exact same thing over here. Add our offset to our base address of our DLL in memory. we get the relative base address for our function offset, and then we are just going to call create remote thread and wait for it. Does this make sense as to how the initial loader works? Any doubts on this? No doubts? Okay. And over here, similar to this, once you call the reflective loader, I will open up, I'll just compile this over here, build, and before I execute this, I will go back to my second solution, that is reflective DLL. As soon as you call reflective loader, our entry point over here is specifically hit. Now, once our entry point here is hit, now this is inside our reflective DLL, and this reflective loader is basically going to be our export address that you have over here. Now we are going to take this offset. Since our offset is executed, we cannot write our main code here. I mean, you can write, but if you are going to write your main code here, you will have to make sure that it is position independent and it does not try to access .data, .r data or anything else over here. But we cannot have that, right? Which means that if you're going to write a really long staged or a staging code, you will need to, sorry, my bad. You will need to find out the relative sections, the other sections that you have over here, like .data, which is your read write data, you have .r data, which is your read only data, and you have to extract these values, and then you might reference these values during runtime, the values that you store over there. And for the same reason, we will have to extract these values, relocate them into proper regions. We will also have to go to the import directory because some executable code over here, we might have called some static functions, and the address or the import address for the static functions rely in the import directory, which needs to be resolved during runtime. So similar to what we did at the export directory here, we are going to do the exact same thing. We are going to walk through each of these, find the first thunk and the original first thunk, try to find out the string name over here, whatever function is being called. We will extract this string name that we have over here, try to find in which DLL does it reside, load that DLL using load library, call get proc address on this loaded library to extract the value of this, and we are going to patch the instruction pointers that we have over here, the keyword value where which will be executing in memory. So in short, our reflective loader that gets executed, it will walk through, load all the DLLs into import directory, relocate itself to a new region, because currently we are in a region where the region is not relocated properly, and you cannot write your own code into a new region if you are already into that region, which means you will have to create another section and copy your current section over there, because you cannot modify yourself unless or else you will have to modify the page permissions for your own region to page read write, which will not work because you also need the execute permission as you're currently also executing, which means you will have to create a new section, copy your section over there, relocate different sections as whatever it is required as per the characteristics of each of the sections that you might have over here. Once you have relocated them, just try to reload, just try to load all the import addresses tables over here, all the DLLs inside this. Once you have loaded and patched the function pointers for each of them, you don't have to worry about anything. Just call the DLL main, and you can add your code inside the DLL main, which is going to be your entry point region over here. So in short, we do the same thing. We create empty structures. We try to call caller. Now caller over here is basically, it returns your return address. Return address is when you call this caller, whatever the address will be in this specific region, that is exactly this address of the DLL into memory. So for example, let's say if I open up Paint quickly, let's assume this is your DLL into memory, and currently you are at this specific location, that is your RDLL that you have over here, or your reflective loader as to where you are currently executing in memory. So when you call the caller function, which calls a compiler intrinsic called as return address, this will return you the address of this specific section that you have, that is somewhere over here on this specific line. Now, once you get this specific section, you don't want this section. What you want is you want to relocate the whole PE to a new region, which means you will need to find out at which specific section or what is the entry point for this specific region, and where this actually ends. So what you're going to do is you're going to do something similar to what we did over here. Since we have an entry point section in our previous code, we loop through it to find the base address. And now since we are also over here somewhere, we are going to subtract -1 till we reach the base address over here. So if you go down, you will see we are doing the exact same thing. Once we get the return address, that is this address over here, we keep on doing -1 till we reach the start. Once we find the entry point over here, that is basically going to be the library address. We are going to read the process environment block. We are going to extract the LDR, the flink, p buffer value, that is going to be the name of the buffer or the Unicode string for this PE, the length of the Unicode string that we have in memory. We are going to perform a ROR operation, because we are going to this ROR operation simply does rotate right. It takes every byte inside this string that we have, converts it, basically flips them to the right side, and tries to create a unique 4-byte hash over here. So we're going to create this and convert it into a 4-byte hash, put it inside this UI value C that we have. We're going to see whether that hash is kernel32.dll, and we are going to take every value in the p buffer that you had, that's your wcar string that we had, convert this wcar string to a hash, try to check whether this hash matches the hash that we already have over here in memory, our raw13 hash. And we'll do this for all of these and try to find each of these values. Once you find kernel32, we will find the kernel base. We will take the base address, try to again loop through it to find the export address directory, similar to what we did earlier over here to find out the function names over here. We'll loop through this, try to find out our functions, load library, get proc address, and virtual alloc in kernel32. Try to find out NT flush instruction cache in NTDLL, because since we are relocating to a new region and two different memory regions cannot have the exact same code normally. So we are going to call the NT flush instruction cache to clear up any existing cache for our current region that is already there. So you can see that once we loop through this, we find the load library, get proc address, virtual hash. We try to find out the ntdll.dll hash. We find out the nt flush instruction cache. Once that is done, we will make sure that we have the addresses for all of them. We will allocate a new region, we're calling virtual alloc, with page rwx region that we have over here. We're going to extract the header size, use a while loop to copy our old region to our new region in a loop. So this just copies whatever region that we have. You can see from the MZ header till there is nothing left. As you can see, it's going minus minus over here. So we're copying everything to the new region that we just allocated, and you can see the new region is the base address over here, which is UI value C. Once we copy this over here, we are going to find the number of sections over here in a while to loop, and we are going to copy the whole section that we have over here. First, we only copied the headers, now the section. Once we copy the section, we'll go ahead and process our import directory that we have. So we're going to find loop through the import directory, find the first chunk and the original first chunk. You can see over here, OFT stands for original first chunk, FT stands for the first chunk that you have over here. We're going to loop through this and try to find out the function names over here, similar to what we did for export address directory. To calculate the RVA, find out the address over here for this specific value. We're going to do the same thing for all of them. And we're going to call load library, which should be, one sec, over here. Yeah, once you find out the name, that is this specific name, we're going to call load library on that. After calculating the name, once you reach over here to original first chunk and you extract this, you're going to call get proc address. And you can see we have called get proc address here. Once you call the get proc address, we'll patch our value that we have over here. That is going to be our first chunk address array. And we're going to patch that keyword value, which means when anyone calls this specific function, it will indirectly go and reach over here, which is similar to what your IIT hooking also does over here. Once we reach over there, we will go ahead and find out basically the image base address over here, loop through this and relocate all our data to a new location as well. All this image address and everything to a new location. Once that has been done, we will call NT plus instruction cache to clear any cache into memory, call the DLL main, and our DLL main is basically where our actual malicious code simply lies over here. That is this specific region. So you can write whatever code you require. So you can see I'm calling load library. which means that if I'm going to call load library, the load library should also be there in my import directory inside kernel32.dll. I think it is not over here. Let me, yeah, sorry, it's kernel32, my bad. I will have to compile this. File, open, day2, reflect to DLL. And if you see here, we should have kernel32, we have load library and get proc address, whatever we are actually calling over there. You can see the reflective loader function, the import directory, and a few all other information over here. Does this make sense as to how this can be executed? To execute this, we will simply go back to A to get the DLL reflection code that we have, DLL reflection.exe, and let me take this code that we have because we are going to reflect this into a target process. Is the DLL that we want to target and process. Let's create notepad, and actually I'll first start process hacker. See what is the PID of my notepad because we already have a notepad up and running. This is the new one, that is 2688, and oh, it was not able to. Okay, that's interesting. Okay, that process did crash, which is interesting. And I'm not sure why we have two of these. Let me just, I cannot see the other notepad running. I think it's running in the background. Ah, my bad. It's actually running over here. My bad. Let me close it. Okay, let me see why it did not run. Let me type C slash Windows slash system 32 notepad.exe. And you can see that our function is called. Just maybe some issue in my PID parsing code. But you can see a load library function called is now executed and it's running properly. Is it clear how it works? Any doubts on the reflective DLL part? Any questions here? No questions? Okay. So yeah, before we start with the unmanaged code part, I'll give you guys some time to play along with this piece of code that we have. And so currently, let me see what slide deck that we have today. Usually people have a lot of questions after this, but I believe everyone understood everything. And we are already at the 24th slide deck. Okay. So any questions or any doubts still here, whatever we have done? Okay, I don't see anyone has any questions. So what I will do is I'll give you guys some time to play along with this piece of code, go through it, let me know if you have any questions. I will answer any question that you might have over here. And yes, after that, we will take our usual break. We'll come back and then we'll continue with the next section of unmanaged code and loading C# and PowerShell into memory after this. So I'll let me know if you guys have any doubts. I'll give you guys around 20 minutes to play along with this, after which we will take our main break and continue with the C# code. I think we'll probably complete our class a bit early today, maybe, because this today was just focused on reflection part. That's the reason. So I'll quickly start a timer. Let me know in case you have any doubts and I will explain them again. 0, start. Oh yes, I think someone asked a question before we get started. The P-based relocation works while doing reflective DLL. How does it work? Okay, the P-based relocation works while doing. Sorry, I did not. I think I did not understand. What do you mean by P-based relocation works? Base relocation, which means like just copying every section that we have over here in the reflective DLL part. One sec. You mean this specific region that we have? We are just copying every region that we have over here. You won't have to worry about this if this looks really complicated. We're not doing something really fancy. Instead of this, what you can simply do is you can actually copy the whole region that you have over here after calculating the import address directory section size, and copy it similar to what we have done over here as well in our while true loop. We are just going to basically taking whatever values we have and copying into our new region. Don't get confused by the similar naming conventions that we have over here. We're just copying our existing region to the new region. Does that make sense? It's nothing fancy. I know that a lot of pointer stuff that you're seeing over here, but all of these can actually be simplified to maybe a while loop where you're just copying your original section to whatever your import directory size is over here, and copy every section into the new section by just extracting the value over here. So you see over here the this is the value, sorry, this is the module name over here there, and this module name starts at this offset that we have. So if we take this offset, check what is the size of this offset. So you should get the size of the add offset over here. As you can see, this is the import directory RVA. There should be an import directory size. As you can see over here, import address table directory size. We are simply going to extract this value, copy every byte that we have from the start of this offset till the offset 3x0 is complete. Sorry, 320 is complete that we have over here. That is the specific section. That's all we are going to do. So don't think that this is something really fancy. It's just the naming convention which can confuse you a lot. Yeah, don't really worry about this, because the naming convention over here is a bit just weird by Stephen Fewer. But in reality, what you're doing is you're just finding the size. So you can see over here that we are trying to find the image directory size that we have. You should be able to find this size, image directory size over here. As you can see, once you extract this size, you're just trying to get the virtual address. The virtual address is inside our sec section, text section over here. That should be over here, as you can see. And if you remember, we extracted this virtual address, calculated the RVA, and copied everything. So we're just going to copy this virtual address to other base region into the new region. As you can see, we're getting the base address for our new for our virtual address, and we're just going to copy every block over here from one region to our new region that we have. You can see we are calling minus minus, which we are just doing nothing but copying over here. This is similar to what we, if I scroll up, you will see another while loop over here where I'm doing minus minus to copy it. You can actually simplify all of this with a simple memcpy by specifying the size, the start point, and the new region location over here itself. This is just a bit too complicated, and I have no idea why he did something like this. A rewrite of memcpy should have been sufficed in this case. Does that make sense? By the way, what I just said, how it is copying everything. We also copied the exact same thing via for our section headers and export directory as well. Does that make sense, Mark? Okay. So I'll start the timer. Let me know in case you have any doubts.